Ooh, I've got a fancy mute button. Ooh. It's the little things that impress me. All right, so it looks like everybody's good to go. We're about finished with chapter 24. I have a couple examples that I wanted to show you in that, so I'm going to go ahead and share my iPad screen. Again, if you don't follow something or if you had a question about something I'm doing, please ask me. I mean, that's the whole purpose of me teaching you guys, so I would much rather you be feeling a little embarrassed, though you shouldn't, by asking me for help than by you actually making a bad grade later and not asking me for help. So please do that. And trust me, if you have a question, probably everybody else will have the same question. So it's really, really helpful for you to ask. That being said, let me go ahead and share my screen. iPad should come up any second now, assuming everything's working properly. And it looks like it is. And for some reason, it's choosing not to show my good notes. Oh, there it is. Okay, now we're on task. Things are good. So, as I said, we were talking about chapter 24, and we're trying to finish that chapter up. And the last thing I talked about, even though I mentioned this a couple times before, for a parallel plate capacitor, capacitance is equal to epsilon 0 A over D. But as I said, if you add a dielectric, and remember, a dielectric is sort of the fancy engineering slash physics word for a non-conductor. So if you add a dielectric to the capacitance, you actually increase the capacitance of the capacitor. And actually, I guess it's technically correct to say add a dielectric to a capacitor as opposed to adding a dielectric to a capacitance. But I think it's pretty uniform either way. You can use that. So if you do add a actual dielectric, then the capacitance goes to C equals K epsilon 0 A over D. Again, that's for a parallel plate capacitor. But the big thing is basically you're going to replace the epsilon 0 with I'm sorry, I used to call this kappa. And I think at some point there might have been a book that used kappa instead of K, but I know Giancoli is definitely using K. So that's why I occasionally slip up and write or say kappa. But another way of looking at this is not saying it's K times epsilon 0, but rather calling it just plain epsilon times A over D instead of K epsilon 0 times A over D. And that is where uh, epsilon is defined to be the dielectric constant times the permittivity of free space. So the epsilon 0 is supposed to be the epsilon 0, and it's 0 specifically because it's dealing with a vacuum. And the difference between it and air, for instance, is for a vacuum, the epsilon 0 is 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. If you wanted to figure out what the epsilon would be for air, you'd have to multiply. You'd have to multiply that epsilon 0 by 1 point, and I want to say it's 0.0006. It might even be, oh, yeah, it's actually three zeros followed by a six. So if you multiplied 8.85 times 10 to the negative 12th by 1.0006, you'd get the epsilon for air. That's why we don't even bother changing it, whether it's air or vacuum. We just treat it the same way. Otherwise, you have to put in the K and multiply it by the epsilon 0. But as I said, the K for air is 1.0006. Paraffin wax, for instance, is 2.2. Polystyrene is 2.6. Paper's 3.7, quartz is 4.3, oil is 4, glass or Pyrex is 5, neoprene or rubber is 6.7, porcelain is somewhere between 6 and 8, mica is 7, water is 80, and strontium titanate, which is a really good one, is 300. Now, the other side of this, as I told you, it also gives mechanical strength, so you can actually take the two plates that which are attracted to each other because one's going to be positive charged and the other one's going to be negatively charged. So they're attracted to each other and they want to tilt over and touch one another. But if you put a dielectric in there, that actually helps prevent them from touching. That's good. So that's another use for it. Not only does it increase the capacitance by a factor of K, it also prevents the two plates from bending towards each other and meeting. But a third thing is that the dielectric strength, i.e., the breakdown electric field strength at which the dielectric becomes a conductor and the capacitor fails, is normally higher than the electric field breakdown strength for air. For air, remember, it's 3 million volts per meter is the electric field strength that actually causes air to become a conductor. But if you look at, for instance, paraffin, that's 10 times 10 to the 6 volts per meter. If you look at quartz, quartz is, well, actually, no, porcelain's about the smallest, and that's still 5 times 10 to the negative 6, whereas air is 3 times 10 to the negative 6. Strontium's not that good far as the electric field dielectric strength. That's 8 times 10 to the 6. But some of them are really, really good. For instance, mica is 120 times 10 to the 6. So that's the other advantage. Now, what we need to know is exactly what happens when we put this dielectric in. And there's a couple concept questions and examples that will work. The one thing I want to point out to you is that since C is equal to Q over V, if you go from C0 to C equals K times C0, then you might want to know how did that happen? Well, one way that can happen is C is going to be K times Q over V. And in this case, we're going to say C0 is equal to Q0 over V0. And then you can sort of make a little bit more sense out of it by saying that C is equal to K times Q0 over V0. But another option is C is equal to Q0 over V0 over K, in which case that again becomes Q0 over V, just like this one became Q over V0. So there's at least two ways in which you can accommodate this new factor of K. You can picture this new factor of K coming in because the charge on the capacitance increased by a factor of K, but you can also figure out that this capacitance increased by a factor of K as a result of the voltage across the capacitor dropping by a factor of K. So that's what those two equations are showing, and I just wanted to point that out. You could imagine some other scenarios physically or mathematically speaking that what if, for instance, Q goes up by a factor of K over 2 and V goes up by a factor, or excuse me, V goes down by a factor of K over 2. That would still get the same factor K, and it would cancel out the two Q's, and that would be fine as well. Actually, no, that would might even make a, yeah, that's going to make a K squared, so that's not right. But there might be some mathematical way to do it. I don't know of any particular cases where you can do that with a capacitance and have those things change by a partial amount. In fact, all I know from the experience I've had and the literature I've read is that either the K goes up or the V goes down, and that's it. So just keep that in mind, but also keep in mind that I didn't tell you definitively whether you could do it some other way. I just know that two ways that does happen is the Q increasing by a factor of K or the V decreasing to V over K. So keep that in mind. Now, with that in mind, I want to go to example, conceptual example 24.1. So first off, I'm going to separate this and say example. Whoa. Actually, I'll say conceptual example. And this is 7. Your book calls it dash. Actually, it's 7. It's chapter 24. What a crackhead. uh, it's example 24.11. Again, your book uses dashes. I use dots. It's not a big deal. But the conceptual example says inserting a dielectric at constant V. So an air-filled capacitor capacitance C0 consisting of two parallel plates separated by a distance d is connected to a battery of constant voltage V equals V0 and acquires a charge Q0. While it is still connected to the battery, a slab of dielectric material with K equal 3 is inserted to fill the space between the plates of the capacitor. Will Q increase, decrease, or stay the same? So I've mentioned this to you before, and I hopefully iterated to you that how important it was, but I want to reiterate it now. Specifically, it's very important to understand that when you leave a capacitor connected to a battery, you've locked the voltage down to whatever the voltage of the battery is. And you are allowing the free charge to move back, or I should say, you have made it free for the charge to move back and forth freely between the battery and the capacitor. It's not, and I'm not using free in the sense that it doesn't cost any energy or anything. I'm just saying that there is a conductive path where charge can increase or decrease on the capacitor plates by flowing into or out of the battery. So that's the scenario, but that's when you keep the battery attached. The Qs can change, but the voltage stays the same. Alternatively, if you disconnect the battery from a capacitor after it's been charged, then you have nowhere for the charges to actually go. So the Q has to stay fixed, but the voltage can vary back and forth. So those are two big concepts that you've got to commit to memory or to understanding or something. Okay. As I said, I'm not a big fan of memorization. I am a big fan of building up paradigms, models, ideas that explain things consistent with the actual evidence. And you might ultimately learn that those models you're using to explain the evidence are actual factual. Okay, that can happen. But the main thing is build a story, build a model, if you will, to make you understand it, and then use that as opposed to just rote memorization. So with this example, what we have is a capacitor that basically has a set area and a set distance of separation. And the area is A, and let's call that A0. And the distance of separation is D0. And the voltage across them is V0. Okay. And that ultimately leads to a charge of positive Q0 and negative Q0 here. And now if we take that same capacitor and instead insert a dielectric whose dielectric constant is 3, then things become a little different, and that's what I'm going to explain to you now. So again, I still have A0, I still have D0, and in this case it says an air-filled capacitor of capacitance C0. So this one corresponds to C0 is equal to Q0 over V0, which equals epsilon 0 A0 over D. Now, in this case, on the right, what I'm going to do is insert a dielectric in there. And this dielectric is going to cause the capacitance to go to C, which equals K times C0. Okay, so that's the capacitance of this capacitor. And it says an air-filled capacitor C0 consisting of two parallel plates separated by a distance. I changed the distance to D0, is connected to a battery of voltage V0 and acquires a charge of Q0. While it is still connected to the battery, a slab of dielectric material of K equals 3 is inserted to fill the space between the plates of the capacitor. Will Q increase or decrease? Now, the other thing I didn't include was the fact fact that the battery is not changing, so I want to go ahead and draw that in here. And we're not disconnecting the battery, so I want to include that as well. So what we're going to do is say, okay, now this voltage is still V0, and what we know is K is equal to 3. Okay? So they're asking, will Q increase, decrease, or stay the same? Because we're keeping the battery in there, connected, V cannot change, but Q can. So we're taking C0, which is equal to Q0 over V0, and that's going to go to C, which equals K times Q0. And we know that the charge can actually change, so we're going to put a Q up there that doesn't have a subscript 0. That means it's potentially a new Q. We just don't know what that Q is. But the voltage can't change, so that has to be V0. And then looking at this, specifically this part right here, tells us that Q must be equal to K times Q0, and that's the actual answer. So Q will increase, and it will increase by a factor of K specifically. Any questions on that? Now I'm going to do conceptual example 2412. I want you guys to read that over, see if you can't come up with the answer already. But here it is. Here's the question. That makes me so mad when it does that. And this is 2412, like that. So in this case, it says, suppose an air-filled capacitor C0 of example 2411 is charged to Q0 and then disconnected from the battery. Next, the same dielectric is inserted between the plates. Will Q, C, or V change? So this time, the battery is disconnected. So that V can change, but Q cannot. So I'm reminding you that once you disconnect it from the battery, it's just two plates isolated in space. Where could the charge at possibly go? Now, there is some answers to that. Obviously, you know, for instance, that water in the air is a polar molecule, and therefore a single water molecule having one side that looks a little bit positive could steal a negative charge away, and a another hydrogen, or excuse me, another water molecule could have its negative side near the positive side. It could steal a positive one. So all that can happen. But in general, if we're just talking about not leaving it for an extended period of time, there's no way the charge can change. What we know is that C0 is equal to Q0 over V0. And what we know is the new C is equal to K times the old C. So that's K times C0. And this has to be equal to the new Q over the new V. But since we know for a fact that the battery is disconnected, then we know the charge can change, but or excuse me, we know the voltage can change, but the charge can't. So I'm going to put the actual Q to be Q0. So now we've got K times C0 equals Q0 over V. And the only way we can actually make this equation work is if we replace the Q, or excuse me, replace the V with V0 over K. And then you'd see by division, Q0 divided by V0 over K becomes K over V0 times Q. So that would give us K times Q0 over V0, which is K times C0. So in this case, C changes and V changes. C0 to K times C0 and V0 to V0 over K. So that's the actual answer for this one. The Q will not change because it has nowhere it can go, at least not in a short period of time. Anybody have any questions on that? Now remember that voltage is the integral of E dot dl. That's the way we calculate voltage. And what we found is, at least in between the plates of a parallel plate capacitor, the electric field is a constant. And if you get a electric field being a constant and you integrate from, one plate to the other, what you see is that voltage going up by a factor of K, or in this case, it actually went down by a factor of K, could be a result of the electric field being decreased by a factor of K, and it turns out that's actually what can do it, or that's one of the ways it can be done. So by putting that dielectric into the between the plates, you are in some sense decreasing the electric field strength by E0, the original electric field strength, over K. So that's something that's going to come up. We're going to make use of that in the molecular description of it. But now I've done these two examples, and it's time to go ahead and work the third example, which comes from the next section. And actually, no, it comes from the same section. It's example 2413. I want to tell you, I highlighted some text, and you should be able to read it because when I highlight parts of the text, I say share the notes, so that should actually show you. But it says the electric field in a dielectric is reduced by a factor equal to the dielectric constant, but the field in a dielectric or insulator is not reduced all the way to zero as in a conductor. Equation 2410, which says the electric field inside the dielectric is E0 over K, is valid inside a dielectric even if the dielectric's thickness is smaller than the gap between the capacitor plates. So what we're going on is, as I hinted at, the reason the voltage can drop from V0 to V0 over K could have been as a result of the electric field dropping from E0 to E0 over K. And this paragraph is telling you that, in fact, in a dielectric of constant K, the electric field in the dielectric will become E0 divided by K, where E0 is the electric field that it had without the dielectric, or E0 is also the electric field that it has outside the dielectric, but still between the plates of the parallel plate capacitor. So now with that in mind, let's go ahead and move on to example 2413. This is an actual computational example. So example 2413 says dielectric removal. A parallel plate capacitor filled with a dielectric with K equal 3.4 is connected to a 100-volt battery. After the capacitor is fully charged, the battery is disconnected. The plates have an area of 4 square meters and are separated by D equals 4.0 millimeters. A, find the capacitance, the charge on the capacitor, the electric field strength, and the energy stored in the capacitor. And then B, the dielectric is then carefully removed without changing the plate separation, nor does any charge leave the capacitor. Find the new values of capacitance, electric field strength, voltage between the plates, and energy stored in the capacitor. So that's the full reading of it. Let me go ahead and write down the material and information that they gave us. So they told us the dielectric constant. I'm going to make all this into 3 sig figs instead of 2. So the dielectric constant is going to be 3.40. The voltage of the battery is going to be 100 volts. And the area of the parallel plate capacitor is going to be 4.00 square meters. And I should make it be known that this 100 volts is actually 100 volts to 3 sig figs. So to do that, I'm going to write 100.0 volts like that. And finally, I have the distance is going to be 4.00 millimeters. So that's the distance. And for part A, they want to know the capacitance. And since we're talking about this is with it being filled, I'm going to call that C as opposed to C0. And I'm going to use a subscript 0 for all the variables that change when the dielectric has been removed. So C is something we want to know. We also want to know the charge on the capacitor, so that would be Q. Again, not Q0 because we're talking about why the capacitor has the has the dielectric in it. The electric field strength and the energy stored. So all of those are questions. And then in part B, we're talking about removing the capacitor, the dielectric from the capacitor, and without changing the plate separation or losing any charge, we're going to find the new values of the capacitance. So C0 is question mark. The electric field strength is E0 is question mark. And the voltage between the plates is V0 is equal to question mark. And the energy stored in the plates is U0. That's also equal to question mark. So that's what we're shooting for here. Now, uh, solution. When you solve this type of a problem, it's really important, and you should do this on your face-to-face test, by the way, is you don't necessarily have to write out the word solution, but go ahead and write down the equations that you're going to be using in their natural form like they appear on the equation sheet, and then somewhere show me exactly which equations you use with the values substituted in with their units. Because if you happen to choose the right equation and plug the right values in, you're going to get the lion's share of the points for that particular test problem. So make sure you do this as regular practice. Also, make sure you draw free body diagrams and other diagrams. For instance, if we need to know the angle of some vector, then you need to have the diagram shown. So if you're calling it theta, we know what theta means as opposed to, phi or the complement of that angle or something like that. So in this case, I'm going to use C. Oops. I'm going to use C is equal to epsilon 0 A over D, and that C, that'd be C0, and I'd say C is equal to K epsilon 0 A over D, which is also equal to, even though I'm not going to need it here, that's also equal to A over D. So that's some of the stuff we're using. We're also going to use U is equal to 1/2 CV squared. And we're going to use maybe, possibly, we could use the voltage delta V is equal to the negative integral of E dot dl. That could come into play, but we're certainly going to use C equals Q over V too. Okay, so those should be the equations we need, and not really sure that we're going to need all of them, but I'm just bringing that out. And by the way, on a test, if you write down an extra equation that you ended up not needing, just draw an X through it or erase it or whatever, and then that way I won't have to take off points for you using quote unquote the wrong equation. Okay, so for part A, we're first asked to find the capacitance, and the capacitance is equal to K epsilon 0 A over D. That is, of course, 3.40. Notice the dielectric constant has no units. The epsilon 0 is 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared, which we could make that coulombs per voltmeter or something along those units, but those lines, but we don't really need that. We know that the area is 4.00 square meters, and we know that the distance of separation is 4.00 times 10 to the negative third meters, like that. So notice I've got everything in the SI base units, which is absolutely necessary for us to figure out what the results are. And of course, by using the base units, the answer comes out in the base unit, and the base unit, of course, would be farads, which is coulombs per volt. So I'm going to take 3.4 multiplied by 8.85 times 10 to the negative 12th times 4 for square meters, and then I'm going to divide that by 4 times 10 to the negative 3, and that's going to give me 3.01. Actually, since I'm using 3 sig figs, I'm going to call this 3.009, and that 9's an extra sig fig, times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the negative eighth farads. So that should be our actual dielectric, or excuse me, our actual capacitance. And that is consistent if we, for instance, if we divided 10 to the negative 8 by 10, we'd get 10 to the negative 9. But in order to do that, we'd also have to multiply the mantissa by 10. So that would become 30.09. So we'd get 30.09 times 10 to the negative ninth farads. That's also true. So C is equal to 3.009 times 10 to the negative ninth, or excuse me, negative 8 farads, but that's also equal to 30.09 nanofarads. So both of those are correct answers. Now we know the capacitance. The next thing we want to figure out is what is the charge? Well, we know the charge is given by C equals Q over V, which gives us Q is equal to CV, which equals 3.009 times 10 to the negative 8 farads times 100.0 volts. And obviously, this gives us 3.009 times 10 to the negative 6 coulombs. And again, that 9 is not a sig fig. And we could call that, of course, 30.0 or 3.009 microcoulombs, and that would be acceptable as well. But I'll just leave it like this. Now we've got Q. The next thing we want to calculate is the electric field. And of course, the electric field is a constant. And we know that the integral delta V is equal to the integral of E dot dl. Or technically, it's the negative integral of E dot dl, but we only care about the magnitude. Since E is a constant, that just becomes E times L. So with that in mind, and I'll restate it this way too, since we're using this, but in a different way than I mentioned it, delta V, at least in magnitude, is going to be E times the integral dl, which equals E times D. So what we know is the voltage has to be equal to E times D, so we can use it that way. So V equals ED implies that E is equal to V over D. Well, V is 100.0 volts divided by 4.00 times 10 to the negative third meters. And of course, that's 100 divided by 4 gives me 25, but then I'm going to multiply that by 1,000. So this is going to be 25.00 times 10 to the third volts per meter is equal to the electric field. So you could also call that 25 kilovolts per meter. That would be acceptable as well. And I think that's the way your book ended up doing it. Yeah, they said 25 kilovolts per meter. Now we need to calculate the energy, and that formula, like I said, there's three versions of it. You can just use C equals Q over V to eliminate the C, or you can use C equals Q over V to eliminate the V. But the formula, the one that I like the best, is 1/2 CV squared. But like I said, to get the other two, you just plug in C equals Q over V to replace the C, or C equals Q over V to replace the V. Using this, we're going to get 1/2 times 3.009 times 10 to the negative 8 farads times 100.0 volts squared. So when I do this multiplication, I get 0.5 times 3.009 times 10 to the negative 8 times 100 squared, and that gives me 1.505. It's actually 5045, and I'm just rounding it to one extra sig fig, and that's times 10 to the negative 1, 2, 3, 4 times 10 to the negative fourth joules, and that's equal to the energy with the dielectric inside the capacitor. So now we have all of the actual values we were asked in part A. Now part B, they're saying we want to actually remove the dielectric and then find the new capacities. Excuse me, the new values, capacitance, and that sort of thing. Uh, Just curious, a parallel plate capacitor filled with dielectric K is connected to a 100-volt battery. After the capacitor is fully charged, the battery is disconnected. So the battery being disconnected means that the voltage can change, but the charge cannot. So for part B, the battery is disconnected. Therefore, uh, Q cannot change. Because of that, we're going to say Q0 equals Q like that. And now we're going to go about calculating the parts that they asked for. So they want to know C0, and C0 is the capacitance of the capacitor without without the dielectric in it. So C0 is equal to the C that we had divided by K. So I'm going to go ahead and take the 30 or 3.009 times 10 to the negative 8 farads, and I'm going to divide that by 3.40, and that's going to give me my capacitance. Of course, I could also just take epsilon 0 A over D and multiply that, but either way would work. 3.009 times 10 to the negative 8 divided by 3.40 gives me 8.85. As you notice, all the numbers cancel out, so we get a mantissa that looks surprisingly like the mantissa of the epsilon 0. So that's 8.85. If I remember correctly, the next digit is 4 in that. So I'll just put that here, just pretending like I remembered for sure that that's it. But I'm just trying to show you that it is instructive to carry one extra sig fig. So this is 8.85 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is times 10 to the negative ninth farads is equal to C0. So since this is a different part, I'll box these off in purple just to make it a little easier for me to quickly find it. So that's what we're calling the capacitance now that the dielectric has been removed. And the next thing we want to calculate is the electric field. And of course, the electric field, or actually, electric field. I could calculate the charge, but we know the charge isn't going to change, so there's no need to do that one. But we could do the electric field, and the electric field is given by E equals V over D, or yeah, E equals V over D. So we'll use that. E is equal to V over D implies E 0, which is what we're talking about now, is equal to the voltage. Now, here's the problem. Uh, the capacitance went up by a factor of K. So what actually caused that? Well, what we know caused that is that since the battery was disconnected, the Q can't change. And since the Q can't change, that means the only way we can change C from Q over V to K times, or excuse me, to C0, which is without that K, is not by changing the Q, but by changing the V. And the only way we can get that is we have to actually increase the V by a factor of 3. So now the V zero over the D zero is what we need. The D didn't change, so I could just leave that as D, but the V zero is definitely going to change to K times V zero, or excuse me, K times V zero. Actually, no, that's K times just a plain V. And then the D is not going to change at all. That's just going to be over the regular D. And therefore, we're now going to get uh, 3.40 for the K times 100.0 volts divided by 4.00 times 10 to the negative third meters. And when I do that math, I get 3.4 times 100 divided by 4 times 10 to the negative 3. And that's going to give me 85.00 times 10 to the fourth volts per meter. Actually, that's times 10 to the 1, 2, 3. That's 10 to the third, technically, since I wrote it as 85. So let me fix that real quick. I was doing that math in my head, and you can see the problem associated with that, obviously. So that's supposed to be equal to the new electric field, which we're going to call just plain E0, because this is the electric field with no dielectric. And I pull that off, and we see that instead of having an electric field that was 25,000 volts per meter, in this case, we're getting it to be 85,000 volts per meter because, like we said, when we put the dielectric in, that decreases the electric field. But that means if we put the dielectric out, that's going to increase the electric field. And that's what we saw. The electric field went from 25,000 volts per meter to 3.4 times 25,000, which is 8.85 volts per meter. Next, we need to do the new voltage, and we just figured out what the new voltage is. The new voltage V is equal to K times the old voltage, and technically I'm supposed to put the zero on the new one and the non-zero on the old one. So now that's going to be 3.40 times 100.0 volts, and that gives me 340.0 volts is equal to V0. I'll box that off. And now we've got the voltage of the new setup. All we're left now with is the U0, which is the energy stored, and that energy stored is going to be U0. Oops, wrong color. U0, still the wrong color. U0 is equal to 1 half C0 V0 squared. In this case, that's going to be 1 half times the C0 is what we found first thing in here. Oh, did I even not do it? Oh, no, there it is. It's 8.85 4 times 10 to the negative 12th coulombs. Oh, that's not 10 to the negative 12th. It just looked the same. So I got to be careful with that. I just saw the 8.85 and jumped. But remember, that's 8.85 times 10 to the negative ninth farads, and then times the 340 volts. So what you see has happened here is the capacitance went down by a factor of 3.4, but the voltage went up by a factor of 3.4. So basically, we're going to take the energy we had and we're going to divide it by 3.4, and then we're going to multiply it by 3.4 squared. So we should ultimately get 3.4 times larger than the energy we had the last time. The energy we had the last time was 1.505. If we multiply that by 3, that would be 4.5. And then times zero point 0.4 would be 0.45. So 4.5 plus 0.45 would be 4.9, somewhere around there. So zero point 0.5 times 8.854 times 10 to the negative ninth times 340 squared, and that gives me 5.118 times 10 to the negative 1, 2, 3, 4, 10 to the negative fourth joules. And that's U0 without the dielectric. So if you take the 5.118 and divide it by the 1.505, you get 3.400 or 3.401. So you can see that that is exactly higher by a factor of 3.40, which is what I predicted by math, not by physics necessarily. Anybody have any questions on that? All right. So your book asks in a note afterwards, where did all this extra energy come from? Uh, and I want to point out to you that when you actually have a dielectric inside of a parallel plate capacitor, what happens is the individual molecules or atoms in the dielectric, if they're polar, then they're going to rotate such that their positive side of their polar molecule or atom is facing towards the negative plate, and then the negative side of their polar atoms or molecule will face towards the positive plate. And that basically makes the dielectric look like it's oppositely charged to each plate. Therefore, those two are attracted. The positive plate is attracted to the negative side of the dielectric, which is the side that's right next to it, and the negative plate is attracted to the positive side of the dielectric, which happens to be right next to it. So when you go pulling that dielectric out, you're actually going to apply some force to break the strength of the force that holds the positive side of the dielectric to the negative side of the plate and the negative side of the dielectric to the positive side of the plate. So you are putting some work into it. And sure enough, if you calculated that work, you'd find that that work is responsible for the additional amount of energy, specifically the 5.1 times 10 to the negative fourth minus 1.5 times 10 to the negative fourth. That would be what's the total work required in pulling it out. And that's why we got that much more energy. Hopefully that seems obvious to you, or not obvious, but it seems reasonable after I explained it. Your book explains it as well, and we're going to talk about that now. So let me show you what I mean about the parallel plates and the dielectrics. So if we imagine that this is the plate of the dielectric and that this is the other plate of the dielectric, I'm trying to make it look kind of uh, wider than it really should be. And I'm specifically doing that so I can make the drawing easy to see. By definition, this width is too big compared to the height. Remember, when we are using the assumption that the electric field between the plates is a constant, then we need the distance from one plate to the other to be a factor of 10 smaller than the distance from the center of the plate to the top edge, or the distance from the center of the plate to the front edge, or to the back edge, or to the bottom edge. Obviously, with me drawing it that far apart, I can't do that. So you got to imagine that these plates are going quite a bit further up, and we're like considering just the middle, and then there's more plate down below as well. So just think about it that way. Now, with that dielectric in there, I'm going to show it with a little gap just so we can see the difference. But the important thing isn't that there's a gap. The important thing is that you see what I'm drawing here. So this is our dielectric slab in here. And just to remind you that this plate goes on that way, I'll just draw a little arrow here and another little arrow here and here. And of course, I'm going to draw another green arrow here saying this dielectric continues on, even though I have it drawn like that's the bottom edge and the top edge. I'm not trying to say that's the edge. I just tried to show it. In fact, it might be better if I do this. Okay, so what's normally happens when you have the plates of a parallel plate capacitor, one side is positively charged, and actually I should write that in blue. One side has a positive charge and the other side has a negative charge like that. And generally speaking, electric field lines are supposed to originate on the positive charge and then disappear on the negative charge. So what we're picturing here is there was a positive charge right here and a negative charge there. Then there's a positive, then a negative, and then a positive, and then a negative, and then a positive, negative, positive, negative, positive, negative, positive, negative. Now, remember, the number of field lines in a given area is an indicator of how strong the electric field is. So if you're actually considering uh, the number of lines, I'll first show you all the lines that go completely across because what I'm trying to do is account for what the dielectric is doing. So I'm going to draw another electric field line from the third set down to the third negative down, again the fifth, and again the seventh. Okay. Now, normally I would have each of those positive signs having a purple line running from it to the negative sign, but because the dielectric's in here, what we're seeing happen is that the polarness of the molecule, and even if the molecule is not polar, this is still going to happen. If the molecule or atom's not polar, we're going to discover that the electrons tend to spend their time closer to the positive plate of the capacitor, and the nucleus of the atoms tend to spend more time away from the positive part because of like charges repelling. So what we're going to have here is a negative side of the atom or molecule closest to the positive plate, and then a similar thing here as well. So in this case, what we're going to get is a purple line that dies on the first negative, and then a purple line that goes from the last positive to the negative on the other side. So now we've got a smaller electric field because you see that at least with the first three lines, that would have normally been three full electric field lines. Now it's only one. Now it's only two full ones and one partial one. So that sort of shows what we're trying to point out. So that's what happens here and here and here and here and here and here. And because of that, we get fewer lines going through it. And inside, we end up getting an electric field that I'm going to call ED. And it's not referring to the purple lines that go all the way, nor is it referring to the purple lines that come to a stop before they get into the green. It's just what the electric field is inside of that plate. So it's actually an addition of the E0 that's been applied to it, and the loss of the E0 electric field lines is taken into account as well. Out here in the space between them has the electric field has a magnitude of E0. So what we're going to do is, going on what we just learned, we found that the electric field strength in the dielectric is equal to the electric field strength that the capacitor had without the dielectric divided by the dielectric. So we know that the electric field strength within the dielectric is the original electric field strength E0 over K. But we also know that this purple vector is the E0, and what we could imagine is, in fact, I'll use a black vector, because this string of positive and negative polar molecules or atoms end with the negative on the left side and the positive on the right side, that creates an electric field pointing the opposite way. So what we can do is we can say, oh, this is the electric field in the dielectric, like that. That last one I didn't really want to draw because obviously it covers up my plus and minus signs, but I'll just put it right here. We can sort of think of the ED as the black vectors and the EO as the purple vectors, and then the sum of the E0 and the ED gives us or excuse me, the sum of the E0 and the little itty bitty vectors give us the ED. So the electric field inside is going to be actually equal to, oops, need to switch back to my color. The electric field inside the dielectric is going to be equal to the electric field that it had without the dielectric. And I'm calling that ED, but you could also call that E induced if you wanted. But when we do this, we're going to come up with an actual expression that relates the electric field to the electric field inside. So the electric field in the, uh, actually, yeah, let me call that black one. Yeah, let's call that black one E induced. So this black one is, oops, let me write it in black so we'll know which one we're talking about. The black one is E induced, E induced, E induced. And what we're saying is the total electric field in the dielectric is equal to the electric field E0 minus the E induced, which is those black lines. So I'm going to say that this is equal to this E0 over K, which is equal to the electric field of the dielectric, is equal to E0 that was already there and minus E induced, which is the little black vectors. Okay, so if I just take this part of the equation, I get E0 over K is equal to E0 minus E induced, and that gives us that E induced should be equal to, if I pull it on the left hand side and then pull the left hand side over to the right hand side, I get E induced is equal to E0 minus E0 over K, which is E0 times 1 minus 1 over K. So ultimately, our expression, and this is what I was shooting for, is E induced is equal to E0 times 1 minus 1 over K. And of course, the total electric field in the dielectric is E minus E induced, E0 minus E induced. So we can always get that. But the main thing is we wanted this expression. Now, if you just remember that V is equal to the negative integral of E dot dl, and that V is related to the charge, and that electric field is related to the charge, then you'd probably see that it's perfectly reasonable to say that Q induced is equal to the Q that it otherwise had without the dielectric times 1 minus 1 over K. Or you could say that the charge density on the outer surface of the dielectric, sigma induced, is equal to the sigma zero that it would have had without the dielectric times 1 minus 1 over K. So these three expressions are all expressions that we can use from this model of the molecular behavior of the dielectric. So now that we have those expressions, we can use those to do things like calculate the electric field and the capacitance of a capacitor that has a dielectric in it, but the dielectric doesn't necessarily cover the entire space between the plates. And that's what our next example is going to do. So let's start with that now, and this will be example 2414. And this is the last example from chapter 24, by the way. So it says dielectric partially fills capacitor. This is example 2414 from roughly page 707 of your textbook. It says a parallel plate capacitor has plates of area A equals 250 square centimeters and separation D equals 2.00 millimeters. The capacitor is charged to a potential difference of V0 equals 150 volts. Then the battery is disconnected. The charge Q on the plates won't change. And a dielectric K equals 3.50 is, oops, I don't know what just happened there. Sorry about that. That was not helpful at all. Uh, excuse me, the battery is then disconnected and a dielectric sheet K equals 3.50 of the same area A but thickness L equal to 1.00 millimeters is placed between the plates as shown in figure 2418. Determine A, the initial capacitance of the air-filled capacitor. B, the charge on each plate before the dielectric is inserted. C, the charge induced on each face of the dielectric after the dielectric is inserted. D, the electric field in the space between each plate and the dielectric. E, the electric field in the dielectric, and F, the potential difference between the plates at the after the dielectric is added, and G, the capacitance after the dielectric is in place. So now I'm going to write down the information you know that we have been given. You might want to reread the question over again so you'll understand it better. I'm going to write down this stuff. Now's a good time for you to read that. A is equal to 250 square centimeters, which obviously is not going to be that helpful to us. So I'm going to go ahead and convert that to square meters. 100 centimeters is equal to 1 meter, but I have centimeters squared, so I'm going to have to square that. So I'm basically dividing 250 by 10,000. So I can call this 250 times 10 to the negative fourth square meters. I have the area now. The distance between the plates is 2.00 millimeters, so I'm going to say times 10 to the negative third meters. The V0 is equal to 150 volts, and actually I want to make sure that's 3 sig figs, so I'm going to write that as 150.0 underbar. The battery is disconnected, and it gives you a parenthetical there. Then the battery is disconnected, parentheses, the charge Q on the plates then won't change, close parentheses, and the dielectric sheet with K equal 3.50 of the same area A but thickness L equals 1.00 square meters is placed between the plates. So such that A equals 250 times 10 to the negative fourth square meters, and L is equal to 1.00 times 10 to the negative third meters. And what we want is A, we want the initial capacitance, which I'm going to call C0 of the air-filled capacitor. And then B, they want the charge on each plate, which I'm going to call Q0 equals Q equals question mark, and that's because the battery being disconnected means the Q's can't change, so Q0 and Q should be the same quantity. Part C, they want to know the charge induced on each face of the dielectric. In this case, it's a little confusing because it says on the face, so it might make you think they're wanting sigma, the charge per unit area, but no, they want the total charge Q, and that's, excuse me, that's Q induced is equal to question mark. For part D, they're asking the electric field in the space between the plate, between each plate and the dielectric. That is, in fact, our E0 equals question mark. And then E, the electric field in the dielectric, that's E sub D equals question mark, and I want to make sure that you can see that that other one's E0. F is the potential difference between the plates after the dielectric is added. So F is delta V equals question mark, and then G is C equals question mark. So that's what we're supposed to be working out. Again, what we can do here is imagine the dielectric like the capacitor plates like this. Imagine the dielectric is this little space here, and this distance is L, and this distance from here to here is D, and of course both of them have an area A. We can see that we're going to have basically a zero point 0.5 millimeters on one side and a zero point 0.5 millimeters on the other side to make up the difference because L is equal to 1.00 millimeters. Sorry, I wrote meters squared because it's m times m, and d is equal to 2.00 millimeters. Okay, so the equations we'll be using are the usual suspects. We're going to use C equals Q over V. We're going to say C is equal to epsilon 0 A over D. We're going to use delta V equals the negative integral of E dot dl. Uh, and we're not asked anything about energies here, but we are asked, for instance, about E dielectric is equal to E0 times 1 minus 1 over K, and Q induced is equal to, remember we just worked that out, Q induced is equal to Q0 times 1 minus 1 over K. Uh, E0, or E dielectric, is also equal to, and that's E induced, not E dielectric. Sorry about that. I wrote this here and that's not what it's supposed to be. So E dielectric is equal to E0 over K. And I think that's pretty much it. So let's start off with A. We want to know the capacitance without the dielectric. That's epsilon 0 A over D, which equals 8.854 times 10 to the negative 12th. I'm going to leave off the units because we've done quite a bit with the units. I don't think we need to keep showing that. That 4 is not a sig fig. I'm just using it because it's an extra digit. And again, I think I remember that's what's after the 5. The A is going to be 250 times 10 to the negative 4th square meters. And the D is going to be 2.00 times 10 to the negative 3rd meters. And computing all of that, I get 8.854 times 10 to the negative 12 times 250 times 10 to the negative 4. And then I'm going to divide that by 2 times 10 to the negative 3. And that gives me, I don't have enough room over there, so I'm going to write this as 1.107 times 10 to the negative 10th farads is equal to C0. So that's the capacitance without the actual dielectric in place. Now we can use Q equals CV to calculate the charge, and this is going to be the charge that it has without the dielectric. But again, that's going to be the charge after the dielectric because we have the battery removed before we put the dielectric in. So it's going to be also equal to Q. But either way, we get 1.107 times 10 to the negative 10th farads. Remember, a farad is a coulomb per meter, times, in this case, excuse me, it's a coulomb per volt, times, in this case, 150 volts. And since the farad is a coulomb per volt, when we multiply it by a volt, we get a coulomb. So times 150 gives me 1.660 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 10 to the negative 8 coulombs. So we'd say Q equals Q0 is equal to 1.660 times 10 to the negative 8 coulombs. I'll box that off as well. Now for part C, they wanted to know Q induced, so I will say C right here. Q induced is equal to Q0 times 1 minus 1 over K. So we can see that's equal to 1.660 times 10 to the negative 8. Again, coulombs is the unit, but I'm going to leave the units off this time. And actually, I'm making an ugly little exponent over here, so I'm going to try to clean that up a little bit. I could really use some medication to stop me from being so obsessive compulsive, but there we are. 1 minus 1 over 3.50. Okay, so in this case, I get the induced charge, which is the charge on the face of the dielectric. Uh, After we put it in there, that's what it becomes. I'm going to take this 1.660 times 10 to the negative 8, and I'm going to multiply it by parentheses 1 minus 1. Actually, 1 minus parentheses 1 divided by 3.50, close parentheses, and this gives me 1.185 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 10 to the negative 8 coulombs. So you can see it's a little bit bigger than the, or excuse me, where did my other charge go? A little bit smaller than the actual charge on the capacitor itself. And that's our Q induced. I'm going to go ahead and circle that off as well. I'm not getting many questions, so just want to ask anybody have any questions from where we're at right now? All right, let me check my chat. It looks like a couple people have chatted anyway, so I need to make sure I am paying attention to that. Someone said all good. Thank you, Alex. Appreciate that. And I now have the chat open so I can read your stuff. I do see that most of you have chatted me your first and last name, so that's good. Make sure you do that. Now I'm going to go on to part D. In part D, we were asked for the electric field. So we want to know the electric field specifically before we put the dielectric in. So remember, the electric field is equal to the voltage divided by the distance, or alternatively, the voltage is equal to the electric field multiplied by the separation between the plates. So for that, I'm going to say D, we have E0, or actually, I should say we have V0, or since I didn't call it, yeah, I did call it V0. We have V0 is equal to E0 times D. That means E0 is equal to V0 over D, which equals 150.0 volts divided by 2.00 times 10 to the negative third meters. Now, 150 divided by 2 is going to give us 75, and then we multiply that by 1,000. So we're going to end up getting 75,000 volts per meter. So that is 7.50 times 10 to the fourth volts per meter is equal to E0. That's the electric field that would exist before we ever put the dielectric in, but then after the dielectric was in, it would also be the electric field between the plates and the dielectric, whereas ED would be inside the dielectric, as I just drew there. So that gives us the electric field. We're now up to part D. Now I'm going to do part E, the electric field and the dielectric. So for part E, get back to my blue, the electric field in the dielectric. I don't know what's happening to my E's, but it's like they have little strokes and the little letters just aren't lining up right. So ED is equal to the electric field it had without the dielectric divided by the dielectric constant. So that's going to be 7.500 times 10 to the fourth volts per meter divided by 3.50. And that gives us, oops, let's check this. That by 3.5, and that gives me 21,428. So 21,420. Technically, it should round to 29 volts per meter. We only had three sig figs though, so this and this are not sig figs. So we're going to say this is 2.143 times 10 to the fourth volts per meter is the electric field strength in the dielectric. So I can circle that off as well. Now we have part F, which is the voltage. Now remember, the voltage could be quite complicated. That's the part where we have to do an integral. But once we have the electric field, it's actually pretty straightforward. We have delta V equals, if we take the magnitude, I can throw the negative away. It's just going to become the integral of E dot dl. But in each of these cases, it's just the electric field times the length. So this is going to become the electric field times our electric field sub zero, which means the electric field in the space that's not in the dielectric. And that distance, of course, is 2 millimeters minus 1 millimeter. So I'll say 2 minus 1 times 10 to the negative third meters. And that's the electric field strength times the distance on one half plus times the electric field again times the distance on the other half. That takes into account both of them, in other words. Now that I have that, I also have the electric field in the dielectric, and in this case, it's just times the 1.00 times 10 to the negative third meters because that's the actual width of the dielectric. So in this case, I'm going to get 7.5 times 10 to the fourth volts per meter times 1.00 times 10 to the negative third meters plus electric field in the dielectric 2.143 times 10 to the fourth volts per meter times 2.00 times 10 to the negative third meters, and this should come out to 96.4. Let's double check that. 7.5 times 10 to the fourth times 1 times 10 to the negative 3. That gives me 75. 2.143 times 10 to the fourth times 2 times 10 to the negative 3. That gives me 42.86. That's way too big. Don't know why I'm getting that. Uh, the whole gap is 2 millimeters. And then the whole of that is 1 millimeter. Let's see if I got anything else different. 2.14, I got that. I got that. 7.5, 1 to the negative 3. And then that divided by 3.5. D minus L, that works. And D minus, okay. So yeah, this should work out to be the right numbers. It looks like the same numbers I'm getting in here, 7.5 times 10 to the fourth for E0. ED, I'm getting 2.14 times 10 to the fourth. That's the same thing I'm getting here. And this does work out, even though my calculator said something different, it works out to 96.4 volts. And I can't tell you what the extra decimal place would be because I didn't get that calculation, but for some reason that's what the voltage is. So now I can circle that off, and now we can calculate the capacitance because the capacitance is the charge divided by the voltage, and we just calculated the voltage, and the charge, of course, is the 1.660 times 10 to the negative 8 coulombs, and we divide that by the 96.4 volts, and that gives us, according to your book, I'm just going to steal the number, 172 picofarads is equal to the capacitance. I want to point out that if the capacitance had filled the space, the capacitance would be 3.50 times larger than the capacitance that we had without the dielectric. If I take 172 picofarads, which is the 10 to the negative 12th, and divide it by 110, 172 divided by 110, we see that we get 1.56. So it's about 1.56, which is not anywhere, it's not really close to one half of the dielectric constant, because one half of 3.50 would be 1.75, and we're getting 1.56. So it doesn't exactly work out linearly with respect to the thickness of the dielectric versus the width of the plates, or the separation of the plates. Uh, that's it. That is all of chapter 24. I did not get into chapter 25, but that's okay. We'll do that next meeting. Anybody have any questions before you go? You're welcome to stick around. I'm going to wait for the last person to leave in case anybody has any questions, but have a good night, and I will see some people tomorrow, and I'll see other people on Thursday. Don't forget, I've moved the test to next week, so you got to get that worked out. I'm going to send out an email probably tomorrow to let you know what times I will be doing online online proctoring. So that's another option you can do, but I'll try to give them to you for the week after next. So that gives you a whole week and maybe almost 2 weeks to prepare. Alex or
Um,
Anahi, do you have a question?
for this question, you're just gonna put it in your notes, like sorry, in Canvas,
What question is that?
the 2414, the example.
Oh, yes, yes. I put this whole notes that I took tonight. That'll be up on my Google Docs probably within about 10 minutes after I log out.
Okay, that's it. Thank you.
All
Appreciate it.
right. See you,
See
Anahi.
you tomorrow.
All right. That looks like it. So I guess I'll stop sharing and have a good night, everyone. Bye bye. Sorry, can't move my shoulder right, and I always look kind of weird this way. My little T-Rex arm.